Okay, so today we're going to be looking at two more examples of regression and inference, one hypothesis test, one confidence interval. So our first example, do people who make more money pay more for their house? Your intuition might be saying yes, but we've got to back that up with statistics. So researchers obtained a random sample of 30 individuals and recorded their income and the cost of their home. Below is the regression output. Assume the conditions for inference have been met. It says, what is the equation for the fitted regression line? So just to start, we want to make sure we're understanding where all of our values are coming from when we're looking at these regression outputs. So just coming over to the table, we know income is the explanatory variable. So higher income would explain somebody paying or having a higher costing home. So income is going to be our x. Constant, that's our y-intercept. So if somebody makes $0 as an income, what would we predict the cost of our home to be? And again, not something we're super interested in, but the constant coefficient, that's going to be our b naught. Okay, so the coefficient in front of our income, that is our slope. That slope is saying for every increase of x, for every amount that the income goes up, cost, the response variable is going to go up by this much. That's our slope. Okay, and then some of the other values we've got going on here. I'm going to scribble these out just as a habit because we know that we're going to be testing slope since the y-intercept for this example doesn't have a real concrete purpose in the real world. So the standard error is going to be our SE. So this value right here is SE. This one over here is going to be our T, our test statistic. Okay, and that will be all we actually need for this problem. So it's asking what is the equation. So the equation, we need the B naught and the B1. And so we'll go ahead and write that out as we predict the cost of a home. So predicted cost, it's going to start at 438.525. Oops. Okay, and it's going to increase by 0.511, and let's just round that up to 5. And so that's going to be times our explanatory variable, which is again a person's income. Okay, that would be your fitted regression line. Again, unless it says least squares regression line, just stick with the general regression line term. Okay, so down here it says conduct a hypothesis test for the slope of the regression line. Define your parameter, and remember you can only take the p-value from the output if it is a two-tailed test. So let's see what type of test this is. So we'll go ahead and state our hypotheses first. My null hypothesis for these regression hypothesis tests is always that the slope is 0, which means there's no linear association between these two things. My alternative, let's look back at the original problem to see what we're trying to test. So at the beginning it said, do people who make more money pay more for their house? So they're hypothesizing a positive association, right? More money as x is increasing, more for their house. Y is increasing. As x increases, y increases. So that's going to be an alternative of beta 1 being greater than 0. Well, what is beta 1? Let's go ahead and define that off to the side. Beta 1 is the true slope for the regression line for income versus cost. That's what we're trying to predict. If I went out and asked every single US citizen how much money they make and how much their home cost. Not really practical, so we took a sample of 30 individuals. Let's go ahead and label that right now. I took this sample and I'm going to use that sample to try to estimate this this beta 1. Okay. Again, conditions are not going to ruin all chances of passing or not passing this specific question. We're going to not focus on the conditions for this video. So I went ahead and just stated that assume the conditions are met. But if we had wanted to check the conditions, we would have needed to look at the residual plot, the original data, and the normal probability plot. All of those things would have had to be provided by the problem. They weren't, so the AP test or the problem that I would give you would have to tell you that the conditions are met, because there's no way to check them based off of the computer output alone. Okay, so conditions met. And we'll go ahead and move on to this, the plan step. Okay, so the plan here is to conduct a linear regression hypothesis test for the slope. So this is lin reg. It's a t-test. We've got t-tests and t-intervals. And I'll go ahead and specify that it's for slope, even though it almost always is for slope. All right, and into the math. So do. This is where we're going to pluck the numbers out. So I'm going to look for the test statistic. I need to report that. That was 22 even. That's nice. Okay. And the p-value, like I explained yesterday, this was not clear, and I apologize for that in the last video. The p-value up here is for two-tailed tests, so I'm not going to use that unless it is a two-tailed test. Again, that says it right here. You can only take the p-value from the output if it's a two-tailed test. Well, it's not. Right down here, looking at our alternative, this is a one-tailed test. So I need to calculate the p-value myself. Okay, the p-value can be found by going into your calculator. And if we draw a picture here just to help illustrate, I know this follows a t-distribution. I got a t-score of 22. Again, this is a very rough picture just to kind of illustrate what the calculator will be doing. The calculator is going to calculate that area underneath the t-curve, the t-distribution. Now, in order for it to do that, we have to give it a certain amount of information. So let's go ahead and look at what that information will be. So second vars is going to take us to our list of distribution functions here on the calculator. So we'll go down to TCDF, that'll be area under a t-curve. It needs a lower bound. Now our lower bound, looking at our picture, is 22. Our upper bound, this is just going to continue indefinitely. So we'll just throw a bunch of 9s in there. And then our degrees of freedom. Our degrees of freedom have to be calculated by taking our sample size and subtracting 2. So let's jump back to our problem and look at the sample size. The sample size is 30. So I'm just going to do 30 minus 2. 30 minus 2 gives me 28. All right, this is going to give us that p-value. So 1.6 times 10 to the negative 19. Okay, that's a very, very, very small number, one of the smallest we've seen in this class. And I want to record that degrees of freedom that I just calculated. Again, that was 28 and minus 2. So finally, we are ready to draw our conclusion. Okay, so I'll type this up, and again, just ask the sub to pause it if you need to slow down. Our decision will be to reject the null because that p-value is so small. And I'm just going to say that it's less than any reasonable significance level. So we have sufficient evidence to say that as income increases, the cost of a person's home increases. Okay. So right here, this is a little bit different because we don't have that third sentence here, but I've done enough to suggest that I understand that there is a positive association, a positive linear relationship. So that's this alternative hypothesis. Beta 1 greater than 0 was my alternative. Just like we've seen in every single hypothesis test up to this point, we have first sentence is decision and justification. Second sentence is we either found evidence or didn't find evidence for the alternative. So I just needed to put the alternative in context. So income increases, cost increases. And that needs an S. Okay, I'll go ahead and just type a second conclusion up here for those of you that want more examples. So what we could have also said we could reject the null because the p-value is less than any reasonable significance level. We have significant evidence to say that there is a positive linear relationship. So as income increases, the cost of a person's home increases. Okay, a couple different options here. I give you guys templates, but they are just suggestions. You don't have to follow them word for word. Again, just decision, justification, and interpretation of that in context. All right, so there you have an example of a hypothesis test for regression. Let's go ahead and look at a confidence interval. So the problem here says, do heavier apples provide more apple juice? Researchers collected a random sample of apples and measured their weight and how much juice they produced in pounds. So we want to be careful here. The table that I have has X and Y a little bit backwards from what we've seen in the past. X is over here on the right, Y is over here on the left. So let's just keep track. The response variable is going to be juice, or juice weight. And the explanatory variable is going to be the apple's weight. All right, the math will not change if you reverse those, but as far as explaining your findings and your results and your statistics, we want those to just kind of remain logical. So the larger the apple, typically the more juice. You wouldn't say, because I had more juice, that explains a larger apple. It just, again, this is the more logical assignment of explanatory and response. Okay, we have the raw data, and we also have our computer output. I've gone ahead and I've entered the raw data in here to show you guys something at the end of the problem, but for right now, we're just going to stick with the computer output, since again, that is the AP preferred style of question for this chapter. Okay, we want to write the line of regression. I'll go a little bit faster for this one. So we're going to predict how much juice we'll get. And we've got our constant. This is our B naught, so that's going to be negative 0.009 plus our B1, which is going to be 0.691, and we're just going to multiply that times the apple's original weight. Okay, again, the emphasis here is not on the conditions. If you want to check the conditions, it's siren. Since you have the raw data, it is possible to do that. You would have to create the scatter plot, and then you would have to look at the residual plot. That's extra work. It is possible that they would ask you to do that, but it is more likely that they would provide you with those tables that we've seen in class, with the pictures already done for you. And again, like I've said, if you forget the conditions or if you can't remember how to check them, then it's completely fine to just move along with the rest of the test or the confidence interval. Okay, we're creating a 95% confidence interval for the slope. So to state, I'm just going to tell the reader that I know the conditions have been met, and I need to define that slope that they're asking me. So this beta 1 that I'm trying to predict or trying to create an interval for, that's going to be what I want to explain in words and in context. All right, so beta 1, this is going to be the true slope of the regression line for apple weight versus apple juice. All right, now that we've stated all that, we're going to plan, and plan just really means tell me what you plan to run in your calculator, or what inference method you plan to use. Well, this is an interval with linear regression, so again, you can just come here and check out stats tests to figure out, well, is it a test or is it an interval? Well, it's a lin-reg t interval, so that's what we'll put. Oops. T interval 4. Again, the calculator can do this for slope or for the y-intercept, so we kind of want to clarify which one we plan to do, even though it's very rare that you would do this for the y-intercept. Okay, and now on to the math. So the do step. Remember, it's always statistic plus or minus your margin of error. So you want to give yourself a cushion in both directions in hopes of capturing that true value, this B1 up here. Sorry, excuse me, beta 1. We're going to use B1 to try to capture beta 1. Okay, this is going to be B1, our sample slope, plus or minus T star times our standard error. All right, well, looking at my original computer output, I can see that B1 is 0.691. And so that's my best guess, and I want to throw a little bit of a cushion out in both directions, so plus or minus T star times my standard error. Well, T star we have to find by considering the distribution. So the T distribution over here, sorry, that's not exactly symmetric. I want to capture that middle 95%. Okay, well, how far do I have to go out in this direction to the left? And how far do I have to go out in this direction to the right before I capture that 95%? Well, the better question is, what is this area over here? That's going to be 0.0 And the reason we have to identify that left tail area is because our calculator is going to need to know when to stop adding up all that area under the curve. So it's going to add up, add up, add up, all the way until we tell it to stop at 0.025. All right, so we'll go into our calculator. We'll go second vars for all the different distribution types that we've talked about. We're going to go down to TCDF. That's number 6. Oops, that's actually not correct. So this is now prompting me for a lower and an upper bound. So looking back at my picture, I'm asking myself, well, do I have a lower bound? Maybe. It's -999. I know that's where it's going to start, but I don't know where it's going to end. I don't know where that upper bound is. That's what I'm trying to find. So I must have selected the wrong item in my calculator. So let's go back. Let's go all the way back. And we'll go to second vars. So if it's not TCDF, it must be inverse T. All right, so inverse T is going to ask me for an area. I know that. I just found it in the green. It's 0.025. All right, degrees of freedom. Degrees of freedom depends on my sample size. Do I have the sample size for this problem? Let's read back through. It doesn't look like it was stated, but I have the raw data. So if we count up how many apples they have here in our X list, we see that there are 15 apples that they measured and recorded. So degrees of freedom is always going to be n-2 for these linear regression analyses. And that means that this would be 15 minus 2 or 13. So your calculator needs that information as well. So degrees of freedom equals 13. And let's find that critical score, my T star. Okay, so it looks like it's 2.16 in both directions. So in order to capture, again, just the ultimate goal here, I wanted to capture this middle 95%. And in order to do that, I had to go out 2.16 in this direction and 2.16 in that direction. So that's my critical score, 2.16. And my standard error, we're going to go ahead and pick that up from the computer output. That's going to be, well, which one of these is it? Again, we don't really concern ourselves with the y-intercept statistics. So it must be this one. This is our standard error of the slope. So 0.067, or let's just call that 0.068, we'll round up. All right, so take a second to calculate that, and hopefully you're asking the sub to pause the video as you go along. I am not going to pause, I'm going to keep going, but please do try that on your own. You should end up with an interval of 0.544 approximately, and 0.838. Okay, just depending again on how many decimals you carried out from the computer output. Okay, so we've got our interval. Now what? What do those numbers mean? What do they stand for? 0.544, 0.838, what are those? Well, those are our slopes, what we think the true slope falls between. So let's look at the conclusion. We are 95% confident that as apple weight increases by 1 pound, juice weight increases between 0.0544 and 0.838 pounds. If you go back to the beginning of the problem, both of those stated that they were measured in pounds. Okay, and that would be our interpretation of that confidence interval. All right, so what I would like you guys to do next, if you still have time here at the end of the period, is to take a look at the last example from your packet of chapter 26 notes. It asks you to conduct a hypothesis test. If your hypothesis test leads you to reject the hypothesis, use a null hypothesis, which, spoiler alert, it will, I'd like you guys to then create a 90% confidence interval. Okay? If you finish all of that and still have time, you can attempt part B, which deals with cause and effect of that relationship. All right, I will be back on Monday. You can email me over the weekend if you have any questions, but if I don't get to it by then, I will talk to you all on Monday. Have a great weekend.